Hello everyone, so today we continue moving on with this chapter, infinite sequences and series. In this case, we move on with section 11.3, infinite series. Okay, what is the difference between an infinite series and an infinite sequence? Okay, number one, as opposed to an infinite sequence, let me provide a brief example. So suppose we have the sequence, let's keep it simple, n squared. So we develop a few terms starting at 1 and finishing at infinity. So we are going to start 1 squared, comma 2 squared, comma 3 squared, 4. Okay, give me a second, this is a bit slow. 4 squared, etc. Right? And all we did is just write the terms of the sequence. That is 1 squared is 1, 2 squared is 2, no, 2 squared is 4 rather, 3 squared is 9, and 4 squared is 16, and so on and so forth. Okay, so what are we going to do today in this section? So we are still going to have a general rule given by some expression in terms of x, n, typically given in terms of x, sometimes it's given in terms of k, sometimes it's given in terms of j. Different books use different letters, or sometimes the same book may use different letters as well. So we are going to have a certain rule. However, instead of having curly braces, instead of having these curly braces and the symbols n equals 1 to infinity, we are going to have this uppercase sigma from the Greek alphabet, in which we are going to have starting the sum from the lower limit n equals 1 and all the way to infinity. So if we write the above sequence in terms of a series, we would write it this way. The sum of n squared, and n starts at 1 and goes all the way to infinity. Okay, so we are going to do the following. So we are still going to list the elements: 1 squared, 2 squared, 3 squared, 4 squared, etc. But in this case, unlike the sequence in which we just listed the elements, in a series we are going to add those terms. So we are going to put a plus sign in between each of the terms and add these numbers: 1 plus 4 plus 9 plus 16. Okay, so there are two types of series in this case. Series that, like just the same way as in the sequence cases, the series will converge and diverge. That is, the series will have an infinite sum. In this case, I'm not going to add all the infinitely many terms because I'm not going to be able to add. And besides, look at in this case how big these numbers get every time, bigger and bigger, and 25, 36, 49, 64, 81, 100, etc. get bigger and bigger and bigger. So this, by the way, will be an example of a series that diverges. For series that converges, in some cases, not all the cases, we will be able to find the sums of those infinite series. And if not, which is going to be most of the cases, we are just going to be using some techniques to determine whether one series converges or diverges without even caring what the series converges to, the value. We're not going to care. So we are just going to care whether the series converges. All right. So what are we going to do? So every single series out there has a sequence of partial sums. What do we mean by a partial sum? We're going to do an example, but first let me show you what the bigger picture of this will be. So if we plug in n equals 1, let me use another color so we can contrast this. If we plug in n equals 1 on the series, we are going to get the first term of the series. The second partial sum will be given by plugging in n equals 1 plus n equals 2 to the series. The third partial sum will be given by adding the term obtained by plugging in n1 plus n2 and plus n3. And so on and so forth. If we did this partial sum, the fourth partial sum will be the first term plus the second term plus the third term plus the fourth term, and so on and so forth, and then the fifth term, and so on, and the sixth, and the seventh, and the eighth, and we will add these partial sums. Okay, so again, how do we get this? By plugging in n equals 1, n equals 2, n equals 3, and n equals 4. And we get this by plugging in the nth term. Okay? Now, a sequence of partial sum will converge just like in the previous section if the limit of that general rule related to the sum of the sequence of partial sums. And then in this case, this is very important, the value of the series will also be equal to that limit. Okay, and the most important point here for this chapter is that this is not easy. In fact, it could be impossible with all we know about math, right? So it could be impossible. So that's why later on we will just care about what about whether a sequence converges or diverges. Okay. However, in this section we are going to look at two cases in which we will be able to find those infinite sums. On the other hand, we have the case in which the sequence of partial sum diverges, then the series also diverges. Okay, so what do we need to evaluate an infinite sum? Number one, we need a formula for the sequence of partial sums, which again, this is not necessarily easy. In some cases it could be really hard or even impossible that we wouldn't be able, and then find the limit of that sequence. Okay, so that is the problem. Like I was mentioned, in this case not every single series can be subject to this type of analysis. Only we are going to look in this case at the two special cases that we can find these infinite sums. In this case, the telescoping series and the geometric series. But let's look at one in general before looking at the telescoping series and the geometric series. Okay, so let's show that this infinite series converges. Okay. If you have seen this before, well, maybe you can look at the form of the series. It corresponds to a convergent geometric series. However, we are going to pretend we don't know anything about series, and we are going to go with the definition above about finding a sequence of partial sums. Okay, so this is what I will do. I will expand the series for 4 terms only. Okay, so the series, okay, so for the series, n equals 1 over 2 to the n. I'm going to expand 4 terms, so 1 over 2 to the first plus 1 over 2 to the second plus 1 over 2 to the third plus 1 over 2 to the fourth plus dot dot dot. This goes on forever, and this will be 1/2 plus 1/4 plus 1/8 plus 1/16. Okay, so let's evaluate the partial sums. S1 will be only the term a sub 1, which in this case is 1/2, right? S2 will be the sum of the first 2 terms. Okay, let's label this as A1, A2, A3, A4. So let's add the first 2 terms. A sub 1 plus A sub 2 equals, in this case, 1/2 plus 1/4, which equals 3/4. I'm not going to spend time finding LCDs. I would rather go a little bit quicker on this. S3 will be the sum of the first 3 terms, a sub 1 plus a sub 2 plus a sub 3. A sub 1 plus a sub 2 plus a sub 3 equals 1/2 plus 1/4 plus 1/8. If we add these numbers, we get 7/8. And let's do S4, the partial sum for the first 4 terms. A sub 1 plus a sub 2 plus a sub 3 plus a sub 4 equals the same 1/2 plus 1/4 plus 1/8 plus 1/16, which adds up to 15/16. Okay, at this point you may be thinking, well, this is starting to get tedious. Yes, because number 1, we are expanding terms of a series. Number 2, we are coming up with partial sums which one at a time. Take some time to do. I agree with you. If I were to complain about this, if I were to talk about this now, that's enough. Just 4 terms. We don't need to develop, I don't know, 5 or 9 or 11 terms. No, that 11 sums. That's enough. All right. So let's find a sequence of partial sums, Sn. Okay, suppose we continue this on and on, right, until we get Sn. So this Sn will be given by S1 plus S2 plus S3 plus S4 plus dot dot dot. Okay, and we will find out what that is. Okay, so let's go over here. Okay, so let's write down what we got for S1. So Sn we will try to find a general rule here. So we are going to have 1/2 plus 3/4 plus 7/8 plus 15/16. And just like we did in the previous section, we are going to come up with a general rule. Remember, we were given a sequence and they asked us to develop a few terms. Now, and then afterwards they gave us the sequence of terms, they asked us to find a rule. So this is what we're going to do. And well, looking at the denominators, do you see how they start increasing? 2, 4, 8, 16. Okay, let me rewrite this. This is 2 plus 2 squared plus plus 2 cubed plus 2 to the fourth. That is 2 to the first. But what about the numbers 1, 3, 7, 15? Well, in this case, that is the problem when trying to come up with a general rule for the sequence of partial sums. This is not always easy or even impossible to do. In this case, well, I will just give you the answer for this. So I will write the number 1 as 2 minus 1. I will write the number 3 as 4 minus 1. I will write the number 7 as 8 minus 1. I will write the number 15 as 16 minus 1. Do you see the pattern here? It looks exactly like we had in the denominator. So Sn will be 2 to the first minus 1 over 2 to the first plus 2 squared minus 1 divided by 2 squared plus 2 to the third minus 1 divided by 2 to the third. And 2 to the fourth minus 1 divided by 2 to the fourth. So what do we get here? We get that Sn equals to 2 to the n minus 1 divided by 2 to the n. Okay, so that is the rule. This is our a sub n. So now we are going to find the limit of that sequence. So the limit of s of n as n approaches infinity, and in this case Sn is given by the expression we got earlier here in the previous step. So let's replace with that and write limit of as n approaches infinity of 2 to the n minus 1 divided by 2 to the n. Okay, let's evaluate this limit. Let's split this up into two terms. So the limit 2 to the n divided by 2 to the n minus 1 over 2 to the n as n approaches infinity. In this case, notice how these 2 to the n's divide out, leaving us with the limit of n as n approaches infinity of 1 minus 1 over 2 to the n. Now, see what happens if we plug in infinity to the denominator. This whole term will go to 0, and the only term that survives right here will be the number 1, so the limit is 1. So we just have shown that this infinite series converges, and the sum actually is 1. The sum of this series is 1. So let me write it down here. N equals 1. 1 over 2 to the n equals 1. Again, this won't be possible all the time. In this case, that's why we chose an example that is easy-ish to come up with a sequence of partial sums and create a rule to find its limit. So that's why in the future, again, like I mentioned earlier in this video, on the next section, we are just going to use some tools and tests to determine whether series converges or diverges, but not necessarily determine whether what their actual sums are. Okay, the telescoping series. So that's one very interesting example. It's a series of the following form, in which we have b minus 1 minus b sub 2, b sub 2 minus b sub 3, b sub 3 minus b sub 4, b sub 4 minus b sub 5. So what happens here? So in this case, the second term, notice how it cancels with the third term, and then the second and then b3's cancel, and then b4's cancel, and then eventually be 5s, and so on and so forth. And typically, telescoping series are going to have this form rational expressions with denominators only, with constant terms in the numerator. Okay, so let's show that this series converges, and let's find its sum, by the way. In this case, this is one of the series that will give us the sum of the series. So sigma n equals 1 to infinity of 1 over n minus n plus 1 under 1. So we are going to develop a few terms. 1 over 1. Okay, let me use a more contrasting color. Okay, 1 and 1. Plus 1 over minus 1 over plus 1. That's going to be 2. 2 plus 1. Plus, let me do a few. 1 over minus 1 over plus 1. That'll be 3. And I'm just keep going. Plus dot 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 plus 1 over n minus 1 over n plus 1. Okay, so let's simplify this series, these elements. So this will be 1 over 1, which is 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. And in this case, it would be worth to say that this was obtained using n equals 1. This was obtained using n equals 2. This one was obtained using plugging in n equals 3. And in this case, for the next step, plus dot dot dot. Okay, let me leave more space. Plus 1 over n minus 1 over n minus 1. Okay, now this is the part in which we cancel terms. So I'm going to cancel this negative 1/2 with this positive 1/2, then this 1/3 with negative 1/3 with a 1/3, and then this 1/4 with, how about this invisible 1/4 that it would be here. And then if we continue this on and on, we are going to have another invisible negative 1 over n here that would cancel with this one right here. So the terms that survive in this series are this one and the very last term. This is why they call it a telescoping series, right? Because it's like using a telescope, right? You are the person viewing the object, and then you're viewing the object which is in the farther side of the telescope. So this will be 1 minus, and by the way, this is plus 1, okay? And plus 1, which is in this case Sn. Now let's find the limit of Sn as n approaches infinity. In this case, it will be the limit of 1 minus 1 over n plus 1 as n approaches infinity. And in this case, notice what happens if this is infinity. The denominator is infinity. This goes to 0. So thus the infinite series goes to 1. So the series converges. And this is the sum. Okay. Let's look at another example dealing with telescoping series. So let's show that this series converges. So let's write it down first. So sigma n equals 1 to infinity of 2n minus 1 under 1 minus 2n plus 1 under 1. In this case, I'm not going to spend all the steps to write every single number and simplify. I'm just going to give this the answer to this. If you plug in 1 here, what are we going to get? So 1 times 2 is 2 minus 1 is 1. So 1 over 1 minus 1 times 2, which is 2 plus 1. That is going to be 3. So 1/3. Plus, if I plug in 2, 2 times 2 is 4 minus 1 is 3. Do you see the pattern actually? I think you can see it right away. How are the terms going to cancel? So 1/3 plus 2 times 2, which is 4 plus 1, that's 1/5. Let's do another one. 3. 3 times 2, which is 6 minus 1 is 5, 1/5 plus 1/7. Do we have another one? Plus 1/7. I mean, no, this is supposed to be minus. Okay, there's supposed to be a minus here. Minus plus 1/7 minus ... and then plus 2n minus 1, actually plus 1, to n minus 1, and then plus 2n minus 1 plus 2n plus 1 inside under 1s. So what is going to happen here? Okay, let me make this a little bit smaller so it looks more organized. And let's make this. Okay. So here, the 1/3 cancels the 1/3, the 1/5 cancels the other 1/5, and so on and so forth. See how these cancel? Again, that's how a telescoping series behaves. Okay, so we are going to get the only surviving terms, which are going to be the first and the last. So we get 1 plus 2n plus 1 under 1, which in this case it will be the sum of the partial sums, of partial sequences, right? No, let me rephrase that, the sequence of partial sums. Okay, so limit of s of n approaches infinity. That is the limit of the expression we obtained in the previous step, 1 plus 2n plus 1. And again, notice that if we plug in infinity in the denominator of the second term, that goes to 0. So the only term that survives is the number 1, which is the value that the series converges to, right? So converges. All right, let's look at another type of series, the geometric series. So a geometric series with ratio R is a series of the form, this one right here. Okay, it looks like a lot of terms. An initial term A, and then A multiplied by powers of R every successive term. But how can we visualize this geometric series? You may have seen this before. Okay, for example, suppose we have a square here. That doesn't look like a perfect square. Okay, suppose we want to visualize the sum 1 over 2 to the n, which is 1/2 to the n power. So in other words, common ratio r equals 1/2. In other words, every time you perform one iteration of the series, divide by 2, or multiply by half. For example, if we divide this square into 2 pieces, okay, the first iteration, we would get this. Also, if we divide the square into 2, and then this square into 2, and then one rectangle into 2, and then this into 2, then that into 2, that into 2, etc., etc., etc. Okay, so that's how we visualize a geometric sequence, a geometric series with common ratio r equals 1/2. What about this 1/4 to the n? Okay, I'm going to use a different geometric shape to divide, for example, a triangle. I'm going to divide that triangle in 4 pieces, and this will be a familiar shape for those of us who like video games. Do you see the triforce going on here, right? So the common ratio one-fourth. That is, divide the geometric shape into 4 pieces, and then we can do the same here. Divide that into 4. And then divide this into 4. And then divide that into 4 many times. So that's another way to that's a way to visualize the geometric series, or the geometric behavior of a series. Okay, so how are we going to tell whether a geometric series converges or diverges? We are going to look at the value of r, that is the number inside of the exponent. Okay, if the absolute value of r is less than 1, then the geometric series converge, and we can find the infinite sum using this formula. Otherwise, if the common ratio r is greater than or equal to 1, then the geometric series diverges. And we're done. We don't do anything else. I'll show you some examples. Okay, show that the following infinite series are geometric and find the sum if they converge. So number 1, let's rewrite this in the correct form. By the way, this series, geometric series, always start at 0. At n equals 0. Okay? So, in this case, for letter A, we have our lower limit to be a 0, so we're good. So from here, we also have an invisible 1 multiplying, because if we compare with the form, before we are able to read the common ratio, we have this coefficient I'm highlighting in green, which I have there. So there is an invisible 1 there, which means in this case that A equals 1 and R equals 1/2. So we need to determine whether the absolute value of r, in this case, the absolute value of 1/2, which is 1/2, in this case, is this less than 1 or greater than or equal 1? Well, it's a fraction, it should be less than 1. So in this case, by the criteria here, we can tell that the geometric series converges. Geometric series converges. Okay, now let's find its sum using the formula S sub infinity equals a divided by 1 minus r, in which a is 1 and r is 1/2. Let's subtract a half from 1. We get 1/2 in the denominator. And then dividing by a fraction is the same as multiplying by the reciprocal, which is 2. Okay, so that is the sum. That means that if you expand these terms of a series, 1/2 plus 1/4 plus 1/8 plus 1/16, etc., all the way to infinity, and then you add all these numbers, this sum will be 2. Okay, where did we get this formula? Well, we're not going to prove this result. I think the proof or the derivation is on the textbook, and the idea is to learn how to get familiar how to use this information. So let's look at letter B. So for letter B, well, we don't have to do anything here other than observing what A and R are given the sequence. So A is 3 and R equals 5/2. But in this case, the absolute value of the common ratio, which is the absolute value of 5/2, which is 5/2, is greater than or equal to 1. So because of this, the series diverges and done deal. Okay. Okay, what about the examples C and D? Okay, so for example, C and D, things are going to change, and we will need to be shifting indices, right? Because the reason why we are going to do that is because for this case, the series doesn't begin at n equals 1, just the same way for the same case for letter D, and we have to have this form in order to be able to use the formula that we used earlier in order to find the infinite sum. Okay, so what do we do? Okay, if the lower limit is decreased by m units, then increase n in the general rule by adding m units. If otherwise the lower limit is increase m units, then decrease n in the general rule by m units. Okay, what does that mean? For example, our goal is to have our lower limit to start at 0, but we have a 1. In this case, we would need to subtract 1 in the lower limit in order to get that done. But if we decrease 1 in the lower limit of the summation, we have to add 1 in n in the general rule, which is described by the first rule. Okay, so let's go ahead and do that. So 1 minus 1 is 0. Starts at n equals 0 now, all the way to infinity. And this will be 5 times 3/4 times n times negative 3/4. to the first power. What am I doing here? I am using laws of exponents. Let me recall the law of exponents. A to the m plus n is the same as a to the m times a to the n, which is what I'm doing here. And in this case, I'm going to multiply these two numbers I'm highlighting in yellow. I'm going to multiply 5 times negative 3/4, which will give us sigma n equals 0 of negative 15/4 times negative 3/4 to the nth power. This way, this is in the form sigma ARN, because this one is not in the form that we want, and neither this one is. Okay, so that's why we take a couple more steps rather. So in this case, let's identify A, which is negative 15/4, and R, which is negative 3/4. So by the geometric series test, we take the absolute value of R, which is the absolute value of negative 3/4, which in this case becomes positive 3/4. And in this case, this is a number less than 1, so the series will converge. Okay. Okay, so the series converges, and in this case, it is possible to find the infinite sum, okay, which will be A divided by 1 minus R. In this case, be careful because R is a negative. Notice there's no absolute value here, it's just R itself. So when we plug this in, we are going to plug in negative 15 divided by 4 over 1 minus negative 3/4. Using the smile rule here, we are going to end up with an addition. So that's negative 15/4. And that's 1 plus 3/4. Negative 15/4 equals 7/4, which in this case, the 4s can cancel, and the actual sum is 15/7. Yes, we could get a negative sum. Yes, it is possible. So converges, and the sum is negative 15/7. Let's go over letter D real quick, and then we wrap up this section with the next page. Okay, notice the starting point of this series is not n equals 0, so it starts at n equals 3. So we need to subtract 3, provided we add 3 on the exponent. So rewriting the series, we get n equals 0, 9 times 3/7 to the nth power times 3/7 to the third power. Okay, let's simplify this because our goal is to make this look in the form of sigma a r to the n, which is not yet the form. We're almost there, but it's not quite yet. Okay, so let's take a couple steps. Number 1, let's cube both numbers that we have here. So let's sigma n equals 0 to infinity. That's 9 times 3/7 to the nth power and times 9 over 3. No, not 9. Hold on. 27. 27 over 343, which is 7 cubed. Okay, how did we get those numbers? By cubing oops, not here, by cubing 3 and by cubing 7. Okay, and let's multiply these two numbers to finally get the desired form. So this will be 9 times 27, I get 243. 243 divided by 343 times 3/7 to the nth power. And in this case, we finally have this AR to the n that we wanted to obtain. Now let's identify A, which is 243 over 343, and R, which is 3/7. And by the way, the absolute value of R, which is the absolute value of 3/7, it's equals to 3/7, which is less than 1. So the series will converge. Right? Let's put green for converges. Let's put purple for the one that it diverged. Okay, so the series converges so far. Okay, so now let's find its sum. The infinite sum as infinity. This will be A divided by 1 minus R, in which A is, yes, big numbers, 243 divided by 343 over 1 minus R, which is 3/7. So this is basically 7/7 minus 3/7. I get 4/7. So 243 divided by 343 divided by 4/7, and then dividing by a fraction is the same as multiplying by the reciprocal. 243 divided by 343 times 7/4. In this case, if we simplify this number 1, this will go to, this has a factor of 49. So that's 149. 49 times 4, that's going to give us a total of 196 in the denominator and 243 in the numerator. So that's the infinite sum if we were to develop all these infinitely many terms of the series and add them together. Well, we cannot do that. It's impossible to add infinitely many terms one at a time. But the good news is that we have this formula to find the sum of infinitely many terms of a convergent geometric series. Okay, let's look at the last part, properties of infinite series. Okay, so in this case, suppose we have two series, the infinite series with rule A sub n and an infinite series with rule B sub n. In this case, both have to be convergent, infinite. There's supposed to be an n there that I omitted. Okay, so we can multiply a series by a constant term and just pull the constant outside. That's one way. And we can always add and subtract two series together. However, if we split the series and we find out that at least one of the series is divergent, then the entire given series is divergent. So that's why the requisite for this is that the two given series are convergent. Otherwise, if at least one term diverges, the whole thing diverges. Okay? All right, let's find the sum of each series if it exists. Okay, so let's do some work first of all. Let's split it into two series. 2 times 3 to the n divided by 5 to the n minus 2 to the n divided by 5 to the n. N starts at 1. Okay, n starts at 1. And let's see. Yes, this one is going to take a while, I think. You'll see why. Okay, so we are going to write this sigma n equals 1 to infinity 2 to the 2 times 3/5 to the n minus and 2/5 to the n power. Okay, so in this case, observe that these two infinite series do not begin at n equals 0, so we need to subtract 1 and add 1 over here. Subtract 1, add 1 here. So this will become the following. N equals 0, 2 times 3/5 to the n times 3/5. So this will be 2 times 3, 6/5, minus the other series, which will be, in this case, we are just going to split 2 to the 5th, 2/5 times 2/5. Okay, this doesn't look really nice. Let me erase and write it again. This will be the sum. N equals 0, 2/5 to the n power. Okay, in this case, for the first series, notice, let's keep simplifying. The first series becomes 6/5 times 3/5 to the nth power, n equals 0 all the way to infinity, minus sigma n equals 0 to infinity, 2/5 times 2/5 to the n power. And in this case, well, I'm not going to write the entire setup. Notice I'm going to look at r only. So in this case, r is 3/5, which is less than 1. Good news. This first series will converge. What about the second series? Is it the case? Well, let's find out. R equals 2/5, which is also less than 1, which also converges. So it is possible to find the sums of these big series. So let's call this series A, and let's call this B. So the sum A will be given by S infinity equals A over 1 minus R. Plug in the numbers. This will be 6/5 divided by 1 minus 3/5. Okay. If we simplify this, you should get 3 when simplifying. I'll let you as an exercise to get the intermediate steps from here to this next step. And for B will be the infinite sum of same formula, A equal A divided by 1 minus R equals not 6/5, in this case 2/5, divided by 1 minus 2/5. Okay, so not 2/5, yes, 2/5. And you should get, in this case, 2/3 at the end. So this means that this sum will be 3 plus 2/3, which is the sum of each series. Add up the two quantities, and what are we going to get? You should get 7/3. Final answer. Let's do one more. And we wrap up this section. So in this case, let's do the exact same procedure we did in the previous example. Sigma n equals 0 all the way to infinity. 9 4/5 to the n minus sigma n equals 0 to infinity of 7/5 to the n power. Okay, in this case, we don't need to do anything else. Oh, by the way, this starts at 1. It should start at 1. Accidentally wrote 0. Okay, in this case, I'm not going to shift the index because by looking at these r's, well, this one is larger or greater than or equal 1. So this will be divergent. Even though this is less than 1, which converges, but because of this term, the whole series will diverge. So r is greater than or equal 1, so the series diverges. All right, and this is the end of this section. In the next section, we are going to look at other theories that we were going to determine whether they converge or diverge without finding its sums like the ones we did in this section. We're going to look at the test for divergence, the integral test, the p-series, and the comparison test. There's even more series, but the scope of this course is to just cover a few of the tests. So I'll see you on the next video. Okay, bye.